does a
stationary orbit, how does it like keep the energy still? Because according to, I mean, just Maxwell's theory of electrodynamics, it says that the electron would fall into a nucleus, something like that, right? How exactly?
So let me get all your doubts first, then I'll go for the discussion directly. Tell me, what is the next one?
So, and then there's something called the Moseley's equation, right? The root mu is equal to a into z minus b.
Mm-hmm.
So like the root is like under root is always positive, right? How is there like a negative intercept for that graph minus ab, right? Like in all the graphs I've seen.
Send me the equation. I'll have a look at it and then we'll talk. Okay, so first is quantized orbits. Okay.
Yes, sir, I sent you a photo.
First of all, I'm not sure if this is the exact Moseley's equation, so let me just confirm what is Moseley's equation.
Okay, I guess the intercept. Okay, my bad. Okay, my bad. My dad's clear. He was thinking something else.
Okay, so your doubt is out.
Yes, sir. Yeah.
Okay, all right. So Moseley's, I'm not going to be adding in. Next up, what else do you have as issues?
Sir, how exactly do we catch the lines like reading on a spectrum using a spectrograph?
Repeat your question slightly differently if you can,
Like
or the same way is also fine.
how do we record on a spectrograph? Say using the spectrometer.
Okay, next up.
Uh, yeah, sir. The other dots are basically based on spectrum.
Tell me the other doubts based on the spectrum.
I mean, similar questions. And then one other is like, sir, if we use like an ideal black body for the absorption spectrum, like, will we get a full black product? Or like, because the black body.
Okay, next up.
Yes, sir. That's it. You
Okay. Your atomic structure is shaky as shit, bro. Just an off comment based on the questions you've just asked me right now. Yeah, sorry, my office is basically a studio, so bunch of
Yes, sir.
studios. I sit wherever I get space. So yeah, I think you have seen like one or two of these already.
Yes, sir. Yeah.
And this is another one. This is a picnic studio. Okay. Let's start off with spectrum. So I'm going to just blast through a few things here. Wherever you're losing me, point out then and there.
Okay.
Okay. All right. So when you're going to be talking about atomic spectrum or atomic spectra, what exactly is an atomic spectra? Let's say I'm going to be having a sample of hydrogen atoms. I'm going to be having a source of light. This source of light is going to be something which is going to be technically giving me all possible wavelengths or other all possible frequencies. All right.
Yes, sir.
So I'm going to be having this source of light shining on my hydrogen atoms over here. And we are going to be having the same spectrum of what I expected. This is my source of light. So what I basically sent, what the source of light was sending out, I'm going to be collecting it at the ending over here. So there's going to be a collector. So the collector, what do I expect to see if the hydrogen atoms have not absorbed anything? I expect to see the full spectrum yet again.
Yeah.
What we see is going to be not
Partial.
exactly the full thing. Parts of it are not seen. These parts which are not seen are going to be called as dark bands. These are the parts which have been absorbed by the hydrogen atoms. So the hydrogen atoms here have absorbed a part of the spectrum over here, which was shining on them, or a part of the spectrum. What does that mean? It means that some of the wavelengths or some of the frequencies have been absorbed by the hydrogen atoms. That is basically what that means. And a large chunk is not going to be absorbed. The parts which are absorbed are obviously not going to be seen when you collect the light back at the ending. So that is why they are coming out as dark bands. So the dark bands are the parts which have been absorbed. Now, this is basically, of course, called as the absorption spectrum. Next up, what we do is we stop the source of light. Or you can think of it as switch it off. So when you switch the fellow off, what happens over there is you're basically going to be stopping the supply of energy. So now the hydrogen atoms which are present here, which have gained energy already. So when the hydrogen atoms absorbed energy, they got excited to a higher excited state. So now they have already got extra energy. So once they've got the extra energy, they are now going to be losing that extra energy and they're going to be coming back down to ground state. Okay. So we're going to be having excited hydrogen atoms. So these excited hydrogen atoms now undergo de-excitation. So when they get de-excited, they are going to be throwing out some light. Now that light is going to be collected. All right, that light is going to be collected, and that light is studied very carefully by scientists. When they study this light very carefully, what are they studying in that light over there? They are studying what are the different frequencies obtained. So that is basically what is being studied here. So when they study that, they notice that we are going to be having these lines which are obtained, or these particular light waves which are obtained over here. They are of very, very specific wavelengths and very, very specific frequencies. And that spectrum which is obtained is called as a line spectra because they are of very specific frequencies. And of
Okay.
course, since this is going to be when the hydrogen atoms are emitting energy here, so this is of course going to be called as emission
Emission.
spectra for hydrogen. Now, I'm assuming you know the different parts of the spectra.
Hmm.
Now, in this case here, you asked a question: what is being seen here? How is the spectra being obtained? This is basically how we get the spectra. So now, when you're going to be collecting this light over here, which is coming out, this light which is coming out, this is basically something which was studied by many different scientists, mainly because this is something very complicated and we cannot really get this that easily.
Hmm.
Why? Because each of these lines here corresponds to enormous amount of work which has to be checked, rechecked multiple times. So what happened was the first set of lines which we had basically started looking at were obviously going to be the ones which we could see with our naked eyes. We could see the hydrogen atoms are basically emitting some light directly once they have been given some energy. So that energy has been transformed into some kind of light. Discrete packets of energy. Light is discrete packets of energy here. So that was studied by the dude called Balmer first.
Hmm.
Okay. Next up, they ended up studying this region and the remaining regions. Obviously, each of these lines, they did not know anything about it. They just knew that it is emitting a line, or they just knew it is emitting some light. So each of these lines here corresponds to an amount of light which is emitted. They studied that light which is emitted very carefully. They found out the frequency, they found out the wavelength of each of those things there. That is basically how this is done. This is going to be the emission spectra. How do we do it in modern day now? We have a device called as a spectrometer. Instead of a bunch of scientists coming together individually and then studying it, that spectrometer is like, as a dekhe, it'll give the, what to say, wavelengths and what to say, or the frequencies which are being emitted over there. So it will be able to give you a nice clean printout of this entire emission spectrum of whatever is put inside. That is basically how the spectrometer works. Now, this is the emission spectrum of hydrogen. When you are talking about the finer spectra, what does finer spectra mean? So if I'm going to be looking at a particular line, say n equal to 3 to n equal to 2, which line is this?
Mom.
First Balmer line.
Alpha. Yeah.
So this first Balmer line, when I'm going to be considering this first Balmer line here, this is of course going to be the red line. So this red line over here looked like one particular wavelength or only one particular frequency when they were studying this for the first time early on. Then when they ended up making better devices where they could make better measurements, they realized this is not one line, this is actually three different, slightly different red lines. Basically think of it as slightly different, three different shades of red. So it looks like red only, it is still red only, but when you are basically, for instance, a red, which this is a red color here, correct?
Yeah.
If I'm asking you what is the color, you and I will bluntly tell red. If I go talk to my daughter what is this color, she will say crimson red or dark red. If I go to somebody else, they will basically have a different shade associated with it, right? Because
Yeah.
they are having a better palette.
Yeah.
They understand colors better than me and you probably. So they are able to distinguish and differentiate it. Why? Because they have already got better devices, better ways to segregate it. So me and you are not that particularly good, let us say. So that is basically what happened. So what was originally looking like one type of red light was assumed to be, or rather was calculated to be, one level of frequency or wavelength. But when they got better devices, better measuring devices, better measurements available, they basically broke it down and they realized, oh, this is not one line, this is multiple lines. That is called as a finer spectra. Okay. So now this n equal to 3 to n equal to 2 line actually broke down into a set of lines. We'll talk about how many lines this breaks down into in a bit. For now, we don't need to go there. So actually why not? Let me just give you the idea there. So n equal to 3 actually has three subshells, correct? What are the three subshells? 3s, 3p, 3d.
3. Yes.
N equal to 2 has which subshells?
2s
2s
2.
and 2p. So when you're going to be having multiple different subshells available, when you want to look at the finer spectra there is a rule which has to be followed. Whenever you are going to be having any transition, there is a quantum condition which has to be applied, which is basically that delta L should be equal to plus or minus 1. Yes, yes, yes. No, 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 I'll take care of it. Close the outside door also. Ra. There will be these disturbances here and there.
Yes, sir.
No, so delta L has to be equal to plus or minus 1. So if delta L has to be equal to plus or minus 1, that basically means you know the L value for SP and DS.
Yes, sir.
So this is a condition which has to be followed. So 3S length we can go down to 2P, 3P length 2S will have a line, and 3D length 2P will have a line. So this was originally assumed to be one line. But in the finer spectra, it becomes 3 lines. What are the 3 lines now? One line from 3s to 2p, one line from 3p to 2s, and the last line from 3d to 2p. This is basically how your finer spectra works. So each of these are going to be very tiny differences in energy. So because the energy difference is very limited or very tiny there, you're going to be having all of them correspond to red. All of them are very, very close shades of red, tinily different shades of red. Now, next up, what do you want to know more about the spectra? What other doubts do you have? Let me quickly talk about what is Zeeman and what is Stark effect as well. So when it comes to Zeeman effect here, what they did was this particular sample of hydrogen, this one, they put a magnetic field. So when you put a magnetic field there, what happens to it is you're going to be having this particular, set of lines which you obtained in the finer spectrum. They split into more lines. They split further into more lines. Now, how many lines? If you want to discuss, I have to discuss a lot more over here. So I'll just tell you for the time being that when you're going to be having a magnetic effect applied over there, finer spectra lines split further. That is basically what happens. Lastly, when you're going to be looking at Stark effect. Stark effect is also sometimes called as the abnormal Zeeman effect. What happens is he ends up putting an electric field. Now, an electric field is something which will simulate or induce its own magnetic field also simultaneously. So there is no electric field separately. So you're going to be having this electric field here is going to be having a magnetic field also obviously attached to it. So this will basically split the Zeeman lines into two each. That is basically what happens. Okay. So now, for instance, this is basically what is going to be happening effectively. When I say it splits, what does it mean? It means instead of what was originally one line or one frequency or one wavelength, it looks like two. Now, let me explain for Zeeman quickly over here why it is happening that way so that you have some clarity. We'll continue with the same analogy over here where we talked about n equal to 3 to 2. So n equal to 3 to 2 was one line in the beginning.
Yeah.
In the finer spectra, it looked like 3. So this 3s to 2p can go from 3s to 2px, or it can go from 3s to 2py, or it can go from 3s to 2pz. Now, under normal conditions, the 2px, 2py, 2pz are degenerate orbitals, which means they have same energy.
Yes. But then, okay.
So, when you put a magnetic field, they will not have same energy though. They will end up having different energies. So, under normal conditions, the 3s to 2px or the 3s to 2py or the 3s to 2pz, they were all same energy. If they were all same energy, they will emit out the same wavelength of light.
Yeah.
So, they look like one line. They are actually going to be same energy here at this condition. So, they emit only one wavelength over there or one type of wavelength. But when you put a magnetic field, the 2px, the 2py, and the 2pz will have different energy levels.
So is it because of the orientation?
We're not going to go into that part right now. I did tell you I'll have to explain a lot more if I have to explain. This is obviously not an explanation. This is just information as of now still. So when you're going to be considering what happens in a magnetic field, the three of them will have different energy. Think of it as every orbital will have different energy in the presence of a magnetic field, external magnetic field. So when you're having an external magnetic field, you will have each of those orbitals having a different energy. So the 3s to 2px line will be different from 3s to 2py, which will be different slightly from 3s to 2pz. So since each of them are different, we get three different lines instead of one.
Hmm. Yeah.
How about the 3p to 2s? How many lines will that break down into?
3px, 3py, 3pz, 2s.
Good. So this is also going to become three lines.
Become 15.
Correct.
Yeah.
So far clear?
Yes, sir.
So
Hmm.
this is basically what happens in Zeeman. Lastly, when it comes to a Stark effect, what do you think will happen? Inside a particular orbital,
Well,
there are two
the
electrons
spin.
normally.
Yeah.
Those two electrons are normally properly, how to say, degenerate. Definitely.
Yes.
But when you are having it in the presence of an electric and a magnetic field from outside, what happens is those two
Mm-hmm.
electrons will also now have different energy.
Hmm.
So every line which you've got in Zeeman will now break down into two more.
Hmm.
Does this clear what's happening so far?
Yes, sir. Hmm.
Next, what else do you have as a doubt in spectra? Any other questions regarding spectra
Oh, sir, like,
or
uh,
whatever else? Please ask.
sir, atomic spectrum, like any atom will always be unique, right? No two atoms will have anything similar.
Repeat your question again.
1 second.
See, if I'm looking at the barcode in a supermarket,
Hmm.
okay, on different items, will the barcode be completely different or will they be different overall?
Different overall, not completely different.
So you have to be very careful with the way you ask your question.
Yeah, that's true. Yeah,
You understand what I was trying to indicate there? Because the way
they'll have
you,
some common and like.
there will be parts which are definitely going to be common. Nobody said that is not going to be there.
Hmm.
The way you phrased it sounded like you're
Yeah,
asking is every bit different.
yeah. I just realized. Yeah, 1 second. Yeah. Okay, then nothing. I got that clear.
Okay, next up, what else we have?
Sir, what? Your voice is not very audible.
Any other questions on spectra?
No, sir. There's nothing.
What other doubts did you have at the starting of spectra?
Sir, what?
What other doubts did you have at the beginning of our discussion on spectra? Why did you? What did you not understand?
No, sir. It was basically just about how, like the other stuff, like how the hydrogen atoms, like how the thing collects the information. But I guess
How do we collect the information? No? You're asking about how we actually collect and find what is the wavelength. Huh?
yes.
Fairly simple. We will end up having light shining out of a hydrogen atom, like say light is shining out of the light behind me over here. I will basically end up measuring how much it is increasing the temperature of some object which I'm going to be holding. Let's say I'm keeping some stuff over here which is going to be simultaneously capable of measuring temperature difference. So I will find out which one is increase the temperature by how much, and that will basically tell me what is going to be the rough wavelength of it, because I'll be getting energy now which has been
Hmm.
absorbed by that object. So if I
Yes.
know the specific heat of that object, its temperature has increased by this much, I was shining the light for this much time, I know the intensity of that light,
Yes,
right?
sir. Yeah.
I'll be knowing how much is going to be the specific heat of this object which has increased its temperature.
So you can find
Using
energy
that I can calculate how much energy has been absorbed,
and then wave them.
then backtrack and go for wavelength.
Okay.
Hmm.
Hmm.
What else? That is just one way. There are obviously going to be many ways.
Hmm. Yes, sir.
The idea there is you can't measure the wavelength directly or frequency directly. What will we measure instead? We'll measure energy.
Energy. Hmm. Okay. Yeah.